Question 5. 2-chloropropanoic acid is used in many chemical synthesis. A. Part 1. An equilibrium is set up when 2-chloropropanoic acid is added to water. Write the equations for this equilibrium. It's better for you to just write the equilibrium without H2O. So you just shows that this 2-chloropropanoic acid it's dissociate and it's formed these ions, this anion and this hydrogen ion. Part 2. 0.15 moles of 2-chloropropanoic acid dissolved in 250 cm³ of distilled water to produce a solution of the pH 1.51. Okay, calculate the pKa for this acid solution. Because the pH of the acid is given 1.51, so from the pH you need to calculate the concentration of hydrogen's ion first. So we know that pH is equal to negative log concentration of H+. So therefore, negative log concentration of H+ equal to 1.51. Okay, so after that, you get this 0.0309 mole per dm³ for the H+. And because this is the acid solution, when X mole of the acid ionized, it will form X mole of the salt and X mole of H+. So therefore, when we know the concentration of hydrogen ion, is actually telling us that the concentration of the salt is the same. So means the concentration of this anion is 0.0309 mole per dm³. Okay, after that, try to use the Ka expression. Concentration of the products over the reactant means in this case is the concentration of the salt times concentration of hydrogen ion over the concentration of acid. Okay, so these two values same, so it's 0.0309 square over this one mole per dm³, because it's given 0.15 mole. The volume is 0.25 dm³, so you just use 0.15 over 0.25. So you get this Ka. So pKa is equal to negative log Ka. So negative log this one, you get 2.80. Part 3. An equal concentration of propanoic acid has the pH 2.55. The 2-chloropropanoic acid is 1.51, which is a lower pH, a stronger acid. So now it's telling you that the propanoic acid is the weaker acid, as is less acidic now. So what is the reason for this acidity? So now explain difference in the pH of the solution of equal concentration of these 2-chloropropanoic acid and the propanoic acid. So the main reason, of course, is the chlorine, right? The chlorine in the 2-chloropropanoic acid. So we know that the chlorine is an electronegative atom. If you withdraw an electron toward itself, when it's withdrawn electron to itself, then the electrons must from somewhere. So the electrons is from the OH here. So the OH now electrons density is lesser, so therefore is weaker and easy to break. So we say that this electron withdrawing group, of course the carbonyl group here also electron withdrawing, but at the same time this is also electron withdrawing. So two effects now. The chlorine now is able to further weaken the OH bond. So when this OH bond is easy to break, then it will form more H+, like here. Okay, more H+. So therefore it's more acidic. So this is the effects of this chlorine. Now the second effect is what? Once it's formed the carboxylate, this one, because the chlorine is still electron withdrawing, is still withdrawing electron toward itself, so the electron density on this oxygen is lesser. So therefore it's less likely to bond with the H plus, and the H plus concentration is higher, so it's more acidic. Okay, so means in another way we say that the chlorine here, because it's withdrawn electron and let the electron density on the oxygen lesser, so we say that it stabilizes the carboxylate ion. Stabilize means let it not to be so reactive or reacts with others. So when it's less likely to react with H plus, so the H plus is more and is more acidic. So again, the effects of this chlorine is weaken the OH bond and stabilize the carboxylate anion. Right. Part B. So now these two chloropropanol acid reacts with the ammonia to form this aniline. So this one is the amino acid, and amino acid, we know that it's going to have its own isoelectric point. For this aniline is 6.1, pH 6.1. Part 1, state what is means by isoelectric point. So very easy. It's the pH. pH. The point is the pH. pH at which amino acid exists as deuter ion. Deuter ion means dipolar ion. Means the hydrogen ion from COOH will gain by the amine to form the carboxylate and the ammonium. And this dipolar ion is actually will make this molecule or this structure neutral. So the deuteron ion is actually charge neutral. So because negative and positive, so it's charge neutral, right? So this is definition. pH at which amino acid exists as deuteron ion, or pH at which the molecule has no overall charge. Give the structural formula of this aniline at pH 2. pH 2, then we need to refer to the isoelectric point, so it's pH 6.1. So means the pH 2 now is relatively more acidic than the isoelectric point. So what happened? The aniline will react with the H plus now. So means the amine group will react with the H plus. So it will form this structure. The COOH will remain and the ammonium will form. So this is a structure of the aniline at pH 2. So you can give this formula, structural formula: CH3 CH bracket, okay, the NH3 positive with the COOH. Part 3. Aniline exists as a pair of optical isomer. The structure of one optical isomer is shown in this figure 5.2. Draw the optical isomer of this aniline. So very easy, you just follow this isomer one, draw its mirror images, make sure these positions is followed. Okay, this one COOH in front and this one same, and this hydrogen at the back, so this one also at the back. So this one CH3 follow this position, and this NH2 also follow this position on right. Okay, now part 4. Polymer C forms from the reactions between the aniline with 4 amino butanoic acid. So this one. Draw a repeat unit of C, the functional group, which is the amide, and this amide should be displayed. So first, you need to arrange the structure. Of course, you no need to do this part, no need to do this part. You need to give this structure only, but it will be helpful when you do this. First, you need to arrange the dipolar or difunctional group on left and right. So it's easier for you to get the structure. For this aniline, we know that the carboxylic acid and the amine. So this is a difunctional group. You just put it left and right. After that, one of the group will react. So let's say the carboxylic acid group reacts. So it will react with the amine group in the 4-amino butanoic acid. So this one is a condensation. The H2O will remove and the new bonds will form. The CN bonds will form. Then it will form the amide bond here. Right? So this left hand side, this part is from the aniline. Right hand side is from this 4-amino acid butanoic acid. And another thing you need to do is to put tails. So put one tails on the nitrogen, show one hydrogen only, and one tail on the carbonyl group. Okay, so this is the polymer chain with one repeat unit, right? Which consists of the 2 monomers. Part 5. State the type of polymerization for this part 4. Okay, it's a condensation polymerization. Very easy. And next one, scientists are investigating C as a replacement for the polypropylene in the packaging. Suggest an advantage using C instead of polypropylene. Polypropylene, we know that is just a hydrocarbon, no carbonyl group there, so therefore it's hard for this polypropylene to decompose. So it's not really that environment friendly because hard to decompose. So why the C means this one? Why this polymer is better? What is the advantage? Because this one has amide group. Amide group can undergo hydrolysis, so it can be degraded. That's why it's better. So C is biodegradable as it can be hydrolyzed because of the amide group. Part C. A student studies the reactions of these 2-chlorpropanoic acid and the ammonia to determine the reactions mechanism. So this one is the reaction 1. The acids with ammonia form the salt and ammonium. Now, identify the conjugate acid-base pair in reaction 1. So it's quite clear that this one is a proton donor, so it's acid, and it will form this conjugate base. So the acid and conjugate base, their difference is 1 proton. Then ammonia here is the proton acceptor, so it's the base, and this base will form the conjugate acid, so the ammonium. So therefore it's very easy. You just need to put the 2 pairs there, so the acid with the carboxylate and the ammonia with ammonium, right? Now next, in an excess of ammonia, so these carboxylates or these anions undergoes nucleophilic substitution. This one is something you learned in the AS last time. So this is the reactions 2, right? Shows the reactions between the ammonia with this anion to form this one. So a student investigated the rate of reaction 2. The student mixed the anion with large excess of the ammonia. So this is a graphs. So from this graph, later we will discuss this one, right? So to prove that it's a first order. Okay, later we'll come back to this. Now, use the graph in figure 5.3 to show the reaction 2 is first order with respect to this anion, this carboxylate. So first order, how we identify or how we shows that is first order when all the half-life they are constant. So half-life constant means that one is a first order. Now from this graph you can easily get the half-life. So the initial concentration is 0.021. Then when the concentration half means 0.0105 somewhere here. So you need to get the you need to get the time from here. So this when concentration half here, so you can get the half-life here. So it's about 500 seconds, the first half-life. So from here to here is 500 seconds. So now 0.0105 will reduce its concentration to half. So let's say to here. When the concentration now half, then we can get another half-life. So get a half-life here. So it's about 1000. So you get this time, right? At this concentration, you get this time, which is 1000. So the second half-life we can get, so we need to use 1000 here, this one, minus 500. So we get the second half-life, so 1000 minus 500, so we get 500. The first half-life is 500, second half-life also 500. So therefore it's a constant half-life. So we can prove that this anion or this carboxylate is first order. So this is the explanation. So the initial concentration is 0.021. Time taken for the concentration reduced to 0.0105, so it means halved, is 500 seconds, so which is the first half-life. The time taken from this 0.0105 mole per dm cube reduced to 0.00525, okay, half concentration, is 1000 minus 500 is still 500 seconds. So now the half-life is constant, therefore it is first order with respect to this carboxylate. Part 3. Explain why a large excess of ammonia needs to be used in order to obtain the result in figure 5.3. Very easy, because when ammonia is large enough, so it won't really affect the rate. So because we don't want ammonia to affect the rate, that's why we put a lot. So eventually any change in the rate will just because of this anion, right? So that's the answer. So we want to make it zero order. That's the reason. So that it will not affect the rate. Now, for part 4, remember, part 4, the ammonia is not in excess. Ammonia now has certain concentration. From this experiment 1 and 2, you need to identify or determine the order of ammonia. So very easy, this question. Use the information in table 5.1, and C part 2 determines whether the nucleophilic substitution is SN1 or SN2. So if you forgot what is SN1, SN2, I tell you a bit of this. SN1 means a nucleophilic substitution which just depends on one reactant only, the concentration of one reactant. SN2 is the reaction mechanism or reaction depends on the two concentration, means if in this reaction it has two reactants, so the rate will affect by the two concentration of this reactant. So means SN1 just depends on one concentration, SN2 will depends on two concentration, the concentration from two reactants. Now, from here, first you need to compare to get the order of this ammonia. So because the concentration of this carboxylate is the same, so just eliminate. Now we can compare this ammonia with the rate. So as you can see, 0.003 to 0.0045 is times 1.5, means it's 1.5 times, and the rate also 1.5 times. Therefore, it's quite clear that the order of ammonia is first order. It's confirmed. So now, from table 5.1, when the concentration of ammonia is 1.5 times, then the rates of reaction also 1.5 times. Therefore, we know that it is first order with respect to this ammonia. Now, if we know that the ammonia is first order and just now already proved this carboxylate also first order, so means both first order, and the rates will affect by both of these reactant. So therefore, we know that we are quite sure that now the reaction proceeds via SN2 mechanism, as the reaction is first order with respect to the carboxylate and the ammonia. So means it proceeds through this mechanism. Ammonia, which is a nucleophile, will donate its lone pair to this partial positive carbon. So after that, it will form this intermediate. The C-Cl bond break, and these electrons, this pair of electrons will move to the chlorine, and it will form the chloride, and the chloride will combine with this hydrogen. The NH bond will break, and this hydrogen ion will combine with the chloride to form HCl, and this is the products that will form, right? So this one means because the first step here, you see, is involved two reactants, right? These two species. Therefore, we say that this is SN2. It needs these two reactants for the reactions mechanism. It means the first step. Now, part 5. Describe the effects of an increase in temperature on the rates of these carboxylates and ammonia. Explain your answer. This is something you learn in AS also. So when temperature increase, we know that the kinetics energy should increase, So therefore, each of the particles will gain more energy and move faster. So what you need to explain is when the temperature increases, the proportion of particles which has the energies more than the EA is greater. Therefore, frequency of effective collision increases, and therefore the rate increases. This is what you learn in AS. It's very easy. And part 6, this part is actually quite challenging, quite challenging for some of you. Now you see, when excess of this carboxylate used, further substitutions reactions occur. One product has a formula, this one, C6H9NO4 2 negative. So these formulas given, and you need to suggest this formula. First, the key is excess of this carboxylate. And because you say that further substitution means we need to use the products from the previous step. What is the products? This one. So it means after the SN2 just now, the products here will further react with the carboxylate. Means this one. So now, this is a reaction. So the products from just now will act as a nucleophile, because this is the amine here, and this lone pair will donate to this partial positive carbon like just now, and after that form this new intermediate. Again, CCl bond break from chloride and the NH bond break. So this pair of electrons restore to this the lone pair on nitrogen. So it will form hydrogen ion combined with the chloride here to form HCl. So after that, it will form these products, these final products, right? So look carefully. So it's actually this one. So after the reaction, it will form this one. Okay, so look carefully. So it's a COO here, COO, CH, CH3, this part, NH, this part, CH, this part, CH3, this part, COO, this part. So therefore you get these products. This is the answer, this one, from mark scheme. So this one is actually this. Okay, I hope you understand. Thank you.